Jessika Trancik is Atlantic Richfield Career Development Professor in Energy Studies in the Engineering Systems Division at the Massachusetts Institute of Technology. Her research centers on evaluating the environmental aspects and costs of energy technologies and setting design targets to help accelerate the development of these technologies in the laboratory. Her projects focus on electricity and transportation with an emphasis on solar energy conversion and storage technologies. She worked previously at the Santa Fe Institute and at Columbia University's Earth Institute. She has a BS in Material Sciences and Engineering from Cornell University and a DPhil in Material Science from the University of Oxford. And she was a reviewer as part of the NREL study that I mentioned earlier. So it's a pleasure to have her speak to us today about rapid innovation and growth in renewable energy.
Okay, thank you, Miguel, and thanks to my hosts for the invitation to be here. I'd like to speak tonight about some recent trends in the growth and development of renewable energy and some implications for the future. And I thought I would start with a bit of motivation for why we're interested in renewable energy, and I don't think this is going to be a surprise to anyone in the audience, but one of the motivations is, of course, to try to mitigate climate change risks. So that's one of the primary motivations, and we recently celebrated the 150th anniversary of John Tyndall's discovery that carbon dioxide traps heat. This is something that one can show on a tabletop or desktop experiment, so that's not something that's debated at all. And the problem is that we're increasing the concentration of this heat-trapping gas in the atmosphere. You can see here in the graph the rapid increase in the concentration of carbon dioxide since the onset of industrialization in the 1880s. And as a result, we're concerned about some of the risks that go along with that. And that includes an increase in the severity and frequency of events such as forest fires, drought, storms, floods, erosion. This is an image of some children jumping over what looks like a rather deep ditch in a village in Alaska. And we'll just pause here for a moment because one of the challenges and one of the really the sad aspects of climate change is that those that have contributed least to this problem, namely they've contributed least to that graph of those increasing concentrations of carbon dioxide, are those that stand to be most hurt by climate change. And that's something that we really should consider because that's something that certainly will be recorded as we move forward. So that's something that those of us that are around today really, I think, need to take into account and think about how we can act accordingly to improve this situation. So what we'd like to do, of course, is to mitigate climate change. And how can you do that? Well, the source of those increasing concentration of carbon dioxide is, of course, the burning of fossil fuels to support human economic activity. And we'd like to continue to support human economic activity, but at the same time reduce emissions. And in order to meet targets that have been set by the majority of leaders around the world, we would have to follow something along the lines of one of these pathways, namely to either, at the time this paper was written, if we had started mitigating or reducing emissions right away, we would have had to have global emissions by 2050. But as you can see, as you wait, the longer you wait, the more rapidly you need to reduce those emissions. And now I should say that we also have to think about how these emissions reductions should be distributed around the globe. And many developed leaders have committed to or have said that they would like to reduce emissions by 80% by 2050. And that's because there's a recognition that those countries that have emitted the most should reduce emissions the most going forward, right? That's a sort of historic responsibility of developed nations. So as was mentioned in the introduction, there's this common target in developing countries, or sorry, in developed countries to reduce emissions 80% by 2050. Now, unfortunately, we're not following that early mitigation scenario, and we're continuing to increase emissions. So this is a report from, or an article from your own CBC, reporting that global CO2 emissions break records ahead of the UN Climate Summit, which has been happening over the last couple of days. And we can see here that, you know, the usual suspects, China, the US, are the largest emitters. Canada is 10th in the world. And so, you know, we're following this path of increasing emissions, and this is sort of the steady path that we've been following for some time now. And primarily, or, you know, about 75% of these emissions are from our use of fossil fuels, right? So then what is the role of renewables? Well, the question is, can we reduce these emissions by transitioning toward low carbon sources, right? And renewables are among those. We also have nuclear, so the three, nuclear, hydro, and other there, are very low carbon sources. And we can see in the case of electricity that they make up about 30% of electricity production on a global level. And if we look at hydro and other, we have about 20% together of renewables. Now, within other is this category of solar and wind, and that's a really interesting category because we've seen high rates of growth in these technologies. So on average, we've seen 30% growth per year in the production of solar and wind for the last 30 years. So that's really, these are really high growth rates. And, you know, I've been working on these issues for some time. And, you know, every year, every conference you go to, you say, oh, well, will this trend continue? And then you see the same people a few years later. It's like, oh, yeah, the trend has continued. But, you know, still, wind and solar, which are included in that other category, still provide a relatively small fraction of global electricity. But we're starting to see signs of that rapid growth. So recently, I gave a talk in Hawaii, and as I flew into Honolulu, I was impressed by all of the solar panels that I saw on the roofs flying in. And so I did a little experiment when I got to my hotel. I said, okay, let me randomly select on Google Earth a Honolulu neighborhood and just see how many solar panels were on the roofs there. And this was the result. So you can see there's really quite a lot of solar panels there. And of course, Hawaii has an incentive to adopt solar. Other forms of, other sources of energy are quite expensive for them. But to reach that 80% emissions reduction target, regardless of what you assume about energy efficiency, now that's not saying that that's not important. We should certainly conserve as much energy as possible. But regardless of whether you follow a sort of path of increasing demand-side energy efficiency, you still need to largely decarbonize your energy infrastructure. And so for the US, for example, to reach that 80% emissions target, and we would see a very similar graph for Canada, regardless of whether you use natural gas, coal with CCS, regular old coal, you see that by 2050, you really need to rely primarily on carbon-free technologies. And those are those technologies that I mentioned, you know, that group of nuclear, wind, and the solar technologies. Now, are they really carbon-free? Let's just take a bit of a reality check. And here, what I'm showing is these technologies in terms of their carbon emissions per unit energy. So that's their carbon intensity. And you can see that those technologies I mentioned, nuclear, wind, PV, solar, thermal, really pretty close to zero. And in fact, as the energy that's used to manufacture these technologies decarbonizes, you would see these points tend to zero. And also on here is the 2030 electricity target for the US and the 2050 target. And those are targets based on commitments that the US has stated they would like to meet in terms of emissions reduction. So the 2050 corresponds to that 80% emissions reduction by 2050. So you can see that there are a number of technologies that have rather low carbon intensity. You can see something like coal with CCS does reduce emissions, and this is with 80% capture. We could look at 90% efficiency of capture. And you still wouldn't quite get below that 2050 target. So even if we transition to coal with carbon capture and storage, which is certainly a good thing, in lieu of coal or even natural gas without, you still need some of these carbon-free technologies. And wind and solar are interesting because there appears to be, or we know that there's a large expansion potential, right? So these are large resources, and so that's interesting. And they're also interesting for another reason, which I'll mention in a minute, which is that their costs have decreased rather rapidly in comparison to other technologies. So current costs, now we're looking at costs, look like this. And with these ranges on here, it looks like they're more or less cost competitive, some of these lower carbon technologies. But in fact, on average, they are a little bit more expensive than some of the other sources. And these numbers, where you are in those ranges, is going to depend on your location and your energy resource, both the resource, the fossil fuel resource, and the renewable resource, and the price of energy from these different conversion technologies. So let's put both of these things then on the same plot, and that will give us our cost carbon curve. And that kind of gives us a picture of where we are today and where we need to go, because really what you would like is these points below that target to really move toward the origin as much as possible, increase in cost. You would like coal and natural gas to come down in carbon intensity, and that may be possible to some extent with carbon capture and storage, but eventually then we would need to transition toward those carbon-free sources that I mentioned. And so you look at this plot, and there are these ranges and these costs, and it looks like, well, some of these renewables are a little more expensive, but this is a static picture. So now let's look at a dynamic picture, and what you're going to see is that in the early years of electrification, so starting in the early 1900s with coal, we had very inefficient plants. And so you'll see the coal data point decrease rapidly on the carbon intensity axis here. And then you're going to start to see some movement on the cost axis. And what will be very evident is really that in recent years we've seen a lot of movement along the cost axis and not so much along the carbon intensity axis, and that is for a good reason. Coal without carbon capture and storage, you can't go below the intrinsic carbon intensity of coal, right? Without capturing it and storing it somewhere. Okay, so here we can see, as I mentioned, rapid decrease in carbon intensity, and that's with increasing conversion efficiency. And then we start to see a few other technologies coming out, and then PV is noted here because of its rapid decline, and that's actually, it's decreased at 10% per year on average over the last 4 decades. And we can kind of zoom in, and then that's our cost carbon curve, and you'll see there's our average, and gas has sort of fluctuated a bit. That's actually gas in 2006, a little more less expensive now. Nuclear costs have actually increased a little bit in the US and also in France. Solar thermal costs have decreased somewhat, and wind costs have decreased as well. So we'll skip over that for now. And now recently we've seen a lot of action along that cost axis. So let's look at the data in a slightly different way and note the log scale there on the y-axis. And so you can see that PV costs have really decreased steadily and really rather rapidly. Wind costs have decreased as well. We see, coal remaining low in cost, somewhat increasing in cost, but really remaining low in cost. And then, of course, in recent years, we've seen this decrease in the cost of electricity from natural gas in the US, for example. Now, if these trends continue, solar could be cheaper than coal after 2020. That's a big if, but there is, based on some of our work, seemingly a lot of potential for further reductions in costs, and so we'll talk about that. Now, if you really want these trends to continue, you would want to continue to support growth of these technologies, and in that case, you would probably need energy storage, so we'll talk about that a little bit later. But one thing you may have noticed in looking at the data in this way is that, and in what I said earlier, that there is a 10% reduction in cost per year, is that these are, the cost of photovoltaics is following an exponential curve, so a negative exponential growth curve. So essentially, it's following the same functional form as Moore's law, and we see that for a number of technologies, that they tend to decrease in cost exponentially with time and with exponentially increasing production. And so this is showing, again, that trend. One thing you can do, and one thing we've done in our research, is to take into account data from lots of different technologies in order to not just forecast future costs of one technology in sort of a deterministic way, but also to try to forecast the expected error associated with that cost forecast. So that's what's shown here. But this is really interesting. I mean, this exponential decline, or this negative exponential growth curve, this exponential decline trend in costs is rather interesting. And as I mentioned, that's been shown for a number of technologies in this paper here. And the conclusion is that Moore's law is not just for computers. These laws actually apply to a number of other technologies. And so that's an interesting area to look into, because it can allow us to say something about how costs might change in the future, given all information we have about the past. Now, of course, you can't ever predict the future perfectly, but you should certainly take the information, historical information, into account if you can. So, what does this mean? Like, what do these trends mean? Well, one thing is that you can now buy 100 times the power with the same amount of money, 100 times the power of PV, from PV, with the same amount of money than as you could in 1975. So for the same dollar invested, I get 100 times more power now than I did in 1975. Because we're now at 1% of the cost that we started out at in 1975. So that's really interesting, and again, it's really fun to go to these PV conferences and just see how things have changed over time. So even 10 years ago, it was a bunch of us, hippies in the room, and then slowly over time, the sort of attire changes, and you can just see like there's more and more money in this industry, and this is an industry that's getting taken seriously, and the predictions are met, cost predictions are met, or sort of these historical extrapolations of cost trends are met, year after year. And then a number of people now, of course, are working on trying to continue to decrease the cost of photovoltaics, and then also develop inexpensive storage so that we could continue to scale up the use of these technologies. Wind is another technology, as I mentioned, that has been increasing in its production 30% per year. And so these are, if you really take these trends to heart, these are actually really interesting and unprecedented observations in the energy sector. We haven't seen this before with other energy technologies. So why can a technology like PV increase so rapidly? Well, there are some hypotheses out there that we're testing in our work. One is that you have a small unit scale, meaning that you can do lots of experiments, many iterations or trials, for less money, and that might contribute to more rapid improvement. The raw materials are a small fraction of the total cost. So for example, as compared to coal-fired electricity, where you have 50% of your cost of electricity coming from the fuel, you have only a small percentage contribution from raw materials in the case of PV. Now, coal-fired electricity, because of that 50% coming from this raw fuel or this traded commodity, which we expect to trend neither up nor down in its price, you have this cost floor that's been imposed. And you can see that here where, after efficiency of conversion sort of leveled off, and this is for US data, you see the fuel cost overall, the black trend, sort of leveling off and trending, and not trending down, trending neither up nor down. And so that fuel cost is what's imposing this cost floor on electricity from coal overall, meaning that these costs are not decreasing, and that's what we saw in an earlier plot. And so with PV, to some extent, with wind, these cost floors are much lower, so you have more room for improvement. So that's interesting, and one of the things we're looking into now is sort of how, if you break down the costs of PV into all of its smallest components, how can we make sensible design decisions going forward to try to increase or to try to sustain and possibly even accelerate these cost reduction trends that we've observed. Now, there's another source of data that also gives us some interesting hints as to where these trends are coming from, who's doing what in the world and why we've seen cost decreases that we have, and that is patent data. One of the things that we did recently was to build a large data set on energy patents globally from all patent offices around the world. And you see some really interesting trends. One is that China is now producing more solar and wind patents than the US. In the 70s and 80s, during the energy crises, we had a lot of investment in R&D, and that drove patent increases. But then more recently, we're seeing that patents are increasing. It appears to be as a result of a whole range of different policies, including those that generate markets or support the growth of markets for these technologies. What you'll notice here is that actually the renewables are overtaking fossil fuels in terms of patenting rates, and that was captured nicely by Wendy Koch, who wrote about this paper and wrote that innovation in solar, wind, and other renewable power is booming worldwide, especially in China, and is now eclipsing that in fossil fuels, an about-face that occurred in just one generation. Right, so that's really interesting. Now, where is this happening around the world? Well, you see different trends in different countries. Japan, for example, is an interesting one because they've continued to support energy and R&D. They weren't, quite so phased by the sort of busts and booms or the energy crises and so forth. So they've sort of continued, been more steady in their support. And as a result, we've seen more steady patenting trends in Japan. And in terms of cumulative energy patents, Japan is still the leader. And you see these increasing trends in solar and wind and a sort of leveling off in coal, oil, and gas in terms of number of patents in Japan. Now, in the US, you see this, but it's exaggerated more, and you also see that increase in coal, for example, during the energy crises, and then sort of a dropping off and then an increase again. And you see this major increase in solar and wind. But now let's look at China, where, these trends are very impressive, where you see, just this large increase in innovative activity in China. And I can talk about that a little bit more if people are interested. So what actually has driven these trends? Where is this coming from? Why are these technologies improving so quickly and growing so quickly, given that, we haven't been very successful in coordinating our efforts globally, for example, to reduce greenhouse gas emissions or support these technologies? Well, it turns out it's coming from a rather disorganized collection of policies that at the global level are driving these trends. So in the early, in the 70s and 80s, as I mentioned, we had that big peak in research and development funding because of concerns related to, the shortage of oil and sort of supply risk associated with oil. And then that funding dropped off precipitously, and we saw this leveling off of patents. But then in recent years, so if we cut off that plot in 1990, you would actually see, or 1995, what you would see is this correlation between R&D funding levels and patenting levels. But since we've extended the plot out further and included this large increase in patents in later years, it doesn't look so correlated anymore. And so what's driving that? Well, what we find is that in this paper is that it's being driven by these policies that support markets and the growth of renewables, as well as R&D. So it's this complex relationship between market growth and R&D. So you have a rather modest a set of public policies, and this really impressive industry response, and that's really what appears to be behind these trends. And as I mentioned, these are kind of disorganized policies, we call them in this paper segmental policies because they're dealing with the supply side and the demand side separately. And there's some challenges with that. So if you really want to control carbon emissions, what you want to do is cap carbon emissions. If you reduce energy demand and reduce carbon intensity of energy separately, you're not going to be as sure that you're going to achieve the same emissions reductions. But that hasn't happened apart from a few contexts, the European Union, for example. But in most places in the US, for example, we don't have a significant, we haven't capped carbon. We don't have a cap and trade system at the national level. But we do have a number of other policies. So, in the US, what is shown here is a proposed policy, and more recently, the Clean Energy Standard. More recently, there's discussion of the EPA regulations. In China, there are a number of supply-side policies driving that growth in renewables, and in the EU and also in India as well. And so this kind of messy collection of policies is what has been driving this growth. So despite all the disorganization, these technologies are growing, and they're really, at a point where they're close to kind of taking off, and they're not quite there yet. And one of the big concerns going forward is storage and the intermittency of solar and wind. But there's also some exciting developments in that area, because once you think about storing electricity, for example, or storing energy, in a chemical form or in other forms, and you don't have to move that technology, that storage technology around, you no longer care about how much it weighs, and so that opens up a lot of different possibilities that we haven't had when we're looking for batteries, for our personal electronics that we're carrying around with us, or our vehicles, where we really care about the battery mass. And so there's some interesting developments there, but we're at this really, this kind of sensitive point, I think, in the development of these markets and in these technologies, where, they're not quite ready to kind of take off on their own in the market. A little bit more investment is needed and a bit more public policy support. And as I mentioned, really the private sector response to modest policies is what's driven these trends. So we need a bit more of that support, some coordinated global policies thrown in there, and certainly a cap on emissions globally would be helpful, but also these policies to support the further development of these rapidly improving technologies that are not quite there yet, but they've done so well in the last few decades. So that in itself kind of argues for continuing to support them. And that cost of that support has been relatively modest. And so these arguments are laid out in a recent commentary article that I wrote, saying that low carbon technologies are getting better and cheaper each year, but continued public policy support is needed to sustain progress. And that's something that I think is important. And again, there are some really interesting areas within that I think we can focus on, like the development of storage technologies, and so forth. So it's this exciting time, and I'm really looking forward to seeing what happens going forward, because you have, on the one hand, disappointment that we haven't moved faster on a global climate policy, but then on the other hand, sort of we're all kind of excited about, and maybe we could even say like pleasantly surprised, at the rate of improvement of these technologies and really the sustained high rate of improvement of the renewables. So that's, I think, really exciting. And in this research, I just want to, before taking questions, acknowledge funding sources and collaborators, and most importantly, my research group back at MIT, and I hope you'll come and visit us if you're in Boston, and I'm happy to take your questions. So thank you for your attention.